all for coming. I'm really happy to be able to introduce to you Dr. Steve Self, who is at UC Berkeley now, but has been all over the world for his career, both for work as well as for research. I was thinking, when did I first know Steve Self? And it was when I was doing my master's, but then I was thinking, when did I not know of Steve Self? And I don't remember a time when I didn't know about his work. So he is just one of the premier volcanologists in the world. He's a fellow of AGU and GSA, a lifetime member of IOVC, which probably doesn't mean very much to many of you, but that's the International Volcanological Society. So we are very blessed to have him here. He's worked at the Open University, the U.S. Nuclear Regulatory something, Berkeley, UT Arlington, New Mexico, all over the world. And that's just where he's worked and taught and based his research from. I think we'll get a sense of the planet that he has covered, plus other work on extraterrestrial volcanoes and lava flows with his talk now. And if you want to hear about more places he's worked after he's talked, I'll work with you to Google that, but get set in because it's a long, long list. And so just very pleased to have him here. Steve, thanks for coming, and take it away.
Thank you, Rachel. Can everybody hear me? At the back?
I'm not sure I pushed the right button. I think I turned it off.
Because I've spent the morning talking about volcanic rocks around here. If I can use a low voice and be magnified, then that'll make me last for the show. Okay.
Oh, no.
All right, well, I'll begin loud, okay? This is about the world's largest type of explosive eruptions, and try to give you what, in my impression, of a realistic picture about them, because there's a lot of fake stuff in the news, I think, that you read. And it'll basically boil down to sort of what we know and don't know about very large volcanic eruptions and the reasons they're quite difficult to have a sort of strong knowledge about. Okay? All of these eruptions are roughly the same, but there are a lot of details that mean there isn't one sort of unique model that fits them all. But almost all of them produce, I hate these things, right? Pyroclastic flows. This is a small pyroclastic flow from Mount Unzen. It's about to overrun some farms here, these buildings. This is a small pyroclastic flow. And they all involve ejection of ash into the atmosphere. This is ash rising off a pyroclastic flow at Mount St. Helens. So Mount St. Helens is here. This is 25 kilometers away. And this cloud rocketed up to 30 kilometers in the atmosphere in 4 minutes. Okay, so its transport up through the atmosphere was subsonic, almost supersonic. So all of these large explosive eruptions do this. On the ground, they form calderas like this. This is part of Toba, which you'll hear about later on in this talk. Large depressions. I think most people will know what a caldera is. And they form fall deposits, which are the light-colored stuff here at the bottom. This is some of the Yellowstone products. And on the top of the fall deposit there are pyroclastic flow deposits formed by these type of phenomena. So these are the types of things we're dealing with for the world's largest explosive eruptions. And put in a word here about hazards, natural hazards in general. And most hazards, earthquakes, tsunamis, hurricanes, we've had a lot of very severe events recently. And we kind of understand them, and we're used to dealing with them because they occur and then they're over very quickly, and the humankind is left to mop up. But a big volcanic eruption will be very different, right? It's not over very quickly. Sorry, go back. They build up. The build-up might be months to years, and might feature small eruptions. We really don't know. The climax could last for hours to a few days, the ash fallout could last for days to weeks. The atmospheric impact could last up to 4 years. The landscape recovery would be decades or longer. We know this from observing recent small explosive eruptions. And the societal effects of something like this, which could affect almost the whole hemisphere, or maybe even the whole Earth, depending on where the volcano is, the societal effect, we're really very, very uncertain about what will happen if there's another very big eruption.
We're going to try it again.
Okay.
You don't have to start.
Test. Yep.
Yes. Very good.
Okay, good? Great, thank you. The media seem to really be desperate for us to have one of these eruptions, right? Here's a web page a few years ago. The Yellowstone supervolcano is the ultimate eruption waiting to happen, right? This is written by a guy called Riff Benton. And, you know, volcanoes are bad, and they really seem, I'll go to the next one. The British newspaper Daily Express seems particularly keen to have us wiped out by a large volcanic eruption. Every time there's a lull in news, they come up with another burp or fart from Yellowstone that's going to be the precursor to the next huge eruption. And it really is quite a sort of unprecedented, alarmist view of what might really happen. And so the rest of the lecture is going to sort of present what we know and don't know about these very large eruptions. And I say that in most natural processes, the bigger something is, the more sparsely it occurs, the rarer it is. And so very big eruptions are very, very infrequent. Let's take a step back. How do we measure eruptions? Well, there are two scales out there. One I'm responsible for. There's the VEI, which we proposed in 1982, based roughly on the volume of the deposit. And then there's the magnitude scale that was proposed very early in Japan in the 1960s, but was picked up by Dave Pyle in the 1998 as a sort of measure for volcanic eruptions, which is based on the mass. And the mass volume relationship with magmas is quite complicated, but I won't go into any details now. Most of this talk, I'll be talking about mass and on the magnitude scale, and super-eruptions or big eruptions are magnitude 7 and particularly magnitude 8. Okay, magnitude 8, more than 10 to the 15 kilograms of magma. These are the real biggies. And these are what people propose that will happen next at Yellowstone. Of course it won't, but we must remember that all of the volcanoes capable of producing a super-eruption also produce small eruptions. And the likelihood that the next eruption is going to be small is much, much higher than the likelihood that it's going to be big. Anyway, another picture of pyroclastic flows here in Montserrat, and recent examples here, Mount St. Helens 1980, which is fresh in my memory, but pre your lifespan for many students these days, is a 5. Tambora, the largest recent volcanic eruption that was of any decent size, 1815, is a 6 or almost a 7. Rinjani, also in Indonesia, 1259, just about a 7. Kikai, Japan, maybe a super-eruption, a magnitude 8, don't know. And then the big super-eruptions. The most recent is Taupo in New Zealand, 25,000 years ago. And I'll spend quite a lot of this lecture talking about the real biggie, the real recent biggie, which is Toba, 74,000 years ago. Okay? Note. Anyway, I think you know, we have had lots of earthquakes, we've had lots of hurricanes, we've had lots of terrible things, tsunami, about as bad as the Earth can give us. But we haven't had any big recent eruptions. And I think this has given us, I've just called it a perception gap here. I don't know a better word for it, a better term for it. But you know, this is a plot of the number of VEI or magnitude 6 and 5 eruptions in the last 200 years before, well, going up to 2020. Note, there's no magnitude 7s, no magnitude 8s on this list. We haven't had one in the last 200 years. And there's only 2 magnitude 6s, okay, Tambora, and this is Katmai and Overrupter in Alaska in 1912, all right? And the rest have been much smaller 5s, Pinatubo in 1991, I'll mention that, Krakatoa in 1883, you've probably heard of that one. They're much smaller eruptions, and during most of the 20th century, there weren't any big eruptions, and so people studying natural hazards sort of don't think about big eruptions as a possible risk. Well, they're too busy dealing with earthquakes and tsunami and other tragedies. Okay. Oh, yes, note. We've had no even 5s this century so far. But just to, rather than show you tables, a picture. This is one of the most large recent events. This is a cloud coming from Puyehue volcano in the Chile-Argentina border. And this was a magnitude or VEI 4 eruption. You can see the eruption column convecting up from the vent that's down here somewhere. You can see a big umbrella cloud spreading above the eruption column. See a helicopter for scale, but this is a 4. You can, what would we don't even realize what a 6 or 7 would be like, such as Tambora and a column height of 35 kilometers or something like that. This reached 15 kilometers in this one in 2011, and this one will be 35, much bigger, much more widespread ashfall, and we've no real experience of dealing with anything like that. This is a silly plot, really, but I think it brings home the point, okay, that most eruptions in the past have been tiny. Okay, I've been on this thing for a minute or two. This is magma volume, linear scale, versus sizes of eruptions. And this is all the recent stuff, Pinatubo, St. Helens, Krakatoa, Tambora. This is the most recent magnitude 8 eruption on this same scale. It's about 500 cubic kilometers of magma, okay, here, which is in New Zealand. It's the one at 26,000 years. And this would be the size of Toba and the size of the biggest eruption that's proposed. And most volcanology textbooks will try and tell you the biggest eruption ever was 28 million years ago in what is now Colorado, called the Fish Canyon Tuff. 5,000 cubic kilometers. And it turns out that a recent study, a more recent study than this one, Rosen Chesner for Toba, has increased the Toba volume to 5,000 cubic kilometers as well, which is quite amazing for such a big eruption, but I'll try and discuss some good reason why Toba may in fact be that size. This is what it looks like on a log. Oops. This is what it looks like on a log scale. Of course, it looks very different, but it allows you to see the sizes of some of the recent historic, subhistoric eruptions. And you might say something. Well, what about Vesuvius, AD 79? Right? Big eruption, wiped out Pompeii and other cities. No, it's not a big eruption. Its magnitude or VEI was probably only a 5. It only involved 3 or 4 cubic kilometers of magma rather than hundreds to thousands of cubic kilometers. It just happens to be that this was a sad case of being in the wrong place at the wrong time. Pompeii, Herculaneum and everything were built at the foot of this lovely volcano called Vesuvius, and when it had a smallish eruption, they happened to be in the path of the pyroclastic flows from the eruption, and they were buried, and everybody was wiped out by the pyroclastic flows. So it's just a sad case, but these aren't big eruptions. Okay, and we have a very poor idea of the frequency of these rare events, and this is something that is key to understanding why these media reports of, oh, there's going to be another Yellowstone super-eruption soon, why they are wrong. Okay, if we look This is the magnitude here, and this is estimates, very crude estimates, and I'll even correct these in this talk, of how many of these eruptions might occur in each period. So for something like a VEI 6, like a Tambora, we might get one every 400 years, something like that. For 200 cubic kilometers, something like the biggest eruption in the Vesuvius area, there might be one every 5,000 years. But by the time we get up to a magnitude 8, you're looking at one every 100,000 years or something. So this is based on very few statistics. There are very few of these events, and if you look back in the past, there aren't many of them to count. So the statistics you can do on them is very poor. Or very, very, I don't know, poor is the wrong word, but very, very hazy. Okay. And another thing is, it's just very difficult to know the true volume of eruptions. And I'll use Pinatubo as a case, okay? Pinatubo, 1991, second biggest eruption of the 20th century. The caldera and the missing volume of the volcano is about 3.5 cubic kilometers. And the estimates for the volume of the eruption are not better known than 3.5 to 5.5 cubic kilometers from the deposits. Most of the ashfall fell in the China Sea and couldn't be measured anyway. So even for the second biggest eruption of the 20th century, we've got like 100% error in the estimates of how much magma was produced in the eruption. We have a very poor idea, even for a smallish, very recent eruption. So what about the bigger ones? I mean, they really are, I won't say they're guesstimates, but they're very poorly based estimates of the volume of these events. This, incidentally, is an interesting picture. If you wanted to see a big eruption, you need to go up in a satellite. Because if you're on the ground near a volcano, this picture was taken in the parking, or from a building of a parking lot on Clark Air Base in the middle of the Pinatubo eruption at midday, okay? In the middle of the eruption, in the midday, and it's black. There's so much ash in the atmosphere, your visibility is almost zero, and you can't see the volcano, which is only about, 15 kilometers from where this picture was taken. And these are pieces of pumice whizzing past the window, illuminated by the flash on the camera. So this is what you would see if you were on the ground trying to see a decent sized explosive eruption. Anyway, we went to Pinatubo, okay? And I usually show this picture. Oops, go back. I usually show this picture because it's one of the few pictures I have of my VEI colleague, Chris Newhall. This is the guy who we worked on the VEI with here. But there's another person here of interest, right? There's Rachel. Oh, there she is. Okay, we're in Pinatubo Caldera. We've walked there. We've walked up a valley after an IAPSI meeting in Bali in 2000. And we had a lovely field trip to Pinatubo to see all the recent deposits there. So there we go. Another question, where might be the next large eruption? And why is that important? Well, the simplest reason is if it's near the equator, the ash and the gases and the atmospheric impact can spread into both hemispheres. If it's more than 20 or 30 degrees north of the equator or south of the equator, then they're going to be limited to that hemisphere. And so it impacts the global spread of the effects of the eruption. Where have we had magnitude 7s and above in the past 200 years? Well, anywhere there's a red dot, which basically is the Pacific Ring of Fire. Right? That's very clear from this picture. Okay? We can go to a longer time scale though. This is going back 2 million years, and they're black dots in this one, I'm afraid. Now we introduce some interesting things, right? Well, we've got the Pacific Ring of Fire, of course, dominating. We've got some over in southern Europe, or in the subduction zones where Africa is impinging on southern Eurasia. But we've also got this cluster in northwest and the western United States. Because we've gone to a longer time scale, we capture some very large eruptions there. So that's where. What about when? Okay. I don't want to dwell too much on this, but here's an attempt using, and this is something I don't understand, extreme value statistics. I've read about it, but I don't really understand it, okay? But I believe what the people tell me, all right? It means that you've got very few cases to count in your statistical analysis, right? This is an attempt in 2010 to estimate the number of magnitude 7 eruptions like Tambora and Rinjani, and it turned out to be 1 to 2 per 1,000 years. And sort of agrees with my previous slide, a little bit like that. And then this is a paper that came out in 2018, once again using statistical techniques like extreme value statistics and a new database called LAMEV for some reason. And this is just the 7s and 8s of the last 100,000 years. And somehow from this data, they produced an estimate that M8s, the magnitude 8 eruptions, were 1 per 17,000 years, and the M7s were 1 per 1,200 years, which is not far, that's not far off my 2 per 1,000 years, but this one is much, much more frequent than I would have got by just looking at the available ages of old eruptions. Even so, 17,000 years is a long, long time, and I don't know what you make of this number. It is much more frequent than other people's estimates of the numbers of large eruptions. Anyway, looking at frequency another way, there was a very nice paper. If you want to know about large eruptions, read this paper. It's by Wilson and others in Nature Communications a couple of years ago. And they looked back 2 million years, and they counted 13 magnitude 8 eruptions. They don't list this one at 7,000 that might be a magnitude 7 eruption. So they can round that up to 15 in 2 million years, so that's 1 for every 133,000 years. 130,000 years. That sort of agrees in my earlier estimate, different from 1 every 17,000 years, but I'm sure they're more frequent than this, because I'm sure there are several large eruptions in this time period that we do not know about on Earth. And the smaller the eruption, the less is our chance of saying, oh, we know about every eruption that's taken place. This paper is also very nice because it shows how variables, now I told you at the beginning that they all produce calderas, they all produce pyroclastic flow deposits, and they all produce ashfall, but apart from that, in just about every other characteristic you can think of, there's no single pattern for super-eruptions. They cover a large amount of variation in any sort of detail, such as magma composition or number of vents and things like this. And so there's a lot of very different things that these eruptions can be produced by. Okay, let's look at, I'm fascinated by this place. I went there in 2018, I've never been there before. This is Toba. It is the youngest really big eruption we've had, and it's only 74,000 years old, only. I mean, that's a long time ago, but there haven't been many other ones younger than it, and it's huge, okay? It's the youngest eruption we're looking at here from this caldera in Sumatra. It's 74,000 years, and the caldera size, it's 100 kilometers long and 40 kilometers wide. It's a very big compression. It has a lovely resurgent block, about which I won't say anything. I'll show you a picture in 3 slides on, taken from a point there, looking this way, down this sort of channel way in the Lake Toba, between the resurgent block and the eastern shore. Okay. Here's a radar image. Shows you the structure a bit simpler, and we're going to see this volcano in this photograph I'm going to show you in a minute. All right, taken from here, and you can see the structure of this. Here's the caldera. Here's the pyroclastic flow deposits. All go to the coast of Sumatra here. They also go to the coast of Sumatra over here. There's another interesting feature, which is this enormous strike-slip fault that runs all the way along Sumatra, and almost, but not quite, intersects the caldera. The caldera is very near this large strike-slip fault, which may explain one peculiar phenomenon about Toba that I'll mention in a minute. How much time? Okay. And it's had eruptions 1 million years ago, 800,000, 500,000, and then this very young one at 74,000. And there's a, when I look at this volcano, it's doing nothing. It's just sitting there. There's no geysers, there's no hot springs, there's a little bit of hydrothermal alteration over here. There's a couple of pathetic lava domes on the resurgent block here. It's nothing like Yellowstone, right? Yellowstone's got lots of hydrothermal features. Why is Toba so quiet and only erupted 74,000 years ago? And Yellowstone so busy and it erupted 2 million years ago. Here's this picture. It's a beautiful place. This is the resurgent block. We're looking down the left channelway of the island, and there's that volcano. That's 80 kilometers from where I'm standing, right? 50 miles away. And this is about half of the caldera. So it's an enormous feature. Okay, moving on. And what I've tried to do here is compare Yellowstone and Toba. So here's, well, you've already seen the pictures of Toba caldera. The dotted line here is the big Yellowstone caldera, right? That area that encloses is very similar to the area that the Toba caldera encloses, but it's 2 million years old. This eruption that formed the big initial Yellowstone caldera is 2 million years old. That's a lot different from 74,000 years old, right? So this is a very young, but strangely inactive caldera. And this is a very old and very active caldera. It's had 3 other younger caldera events going on, the youngest being this one. And this youngest Yellowstone event is 600,000 years ago. So that's an order of magnitude older than Toba. So will Yellowstone erupt the next time, in a big way the next time it goes? No, probably not. No. There's no real global statistics to guide you on this, but almost certainly, because Yellowstone has been very busy building lava domes and having other types of eruptions in between the big eruptions, the next Yellowstone eruption is going to be small, not large. Look at the size, some of these, just impressing with figures. This is an ashfall map of the Pinatubo ashfall. This is Tambora, and this is Toba. And this was, I made this slide 12 years ago or something. Since then, there's been a lovely study by an Italian colleague, and he took all the deep sea sites where Toba ash was formed, and he fitted them to a wind dispersal pattern for this region, and predicted what the fallout would be. And it's very good. And he predicted that the ashfall would be in East Africa, and in fact, this paper was published in 2014. In 2018, there were 2 papers in Nature, one describing Toba ash found in an archaeological site, Lake Malawi in East Africa, and one in the south coast of East Africa. So his map predicted that ash would fall there, and then it was found. We're just waiting for Toba ash to be found in northwestern Australia, right? Somebody will turn it up one day, I'm sure. But this is an enormous ash cloud, and his volume for this, his magma volume to create this ash cloud is 3,800 cubic kilometers of magma, dense rock equivalent. Alone in the fall deposit, that was bigger than the previous estimate for the whole eruption. And if you add that to a reasonable figure for the Toba ignimbrite, you've got a 5,300 cubic kilometer eruption. For such a huge caldera, to me it makes sense. It also means that if Yellowstone has a similar sized caldera, the estimates for the Huckleberry Ridge Tuff, I think that's what it's called, the bigger Yellowstone event 2 million years ago, are vastly underestimated. That's
rife for a study. We know that, well, we'll see in a minute, there's a big Yellowstone ash cloud all over the US. If somebody did a proper job on that and recalculated the volume, I'm sure the Yellowstone volumes for their eruptions would almost double. Right. How do these eruptions work? When did we start? We started one? Okay, great. How do these eruptions work? The main thing is this umbrella cloud, okay, is Mount Redoubt erupting in 1990, okay, and it had two phases. One, they ejected a nice high column, and what happens is the column goes up, the atmosphere is getting colder, and you reach a point where the density of the rising convecting ash column is equal to the neutral, it passes the zone of neutral buoyancy in the atmosphere. And because it's moving up, it will overshoot, and then it will collapse back down, and it will spread out at that level. And so you get this enormous umbrella, almost like a pyroclastic flow in the atmosphere, spreading out from the eruption column, and that will be taken by the stratospheric or upper tropospheric winds and spread around the Earth. This is a smaller neutral buoyancy spreading umbrella cloud from the pyroclastic flow that was produced in the second part of this Mount Redoubt eruption. And so this is rising off this pyroclastic flow that you can see the cloud off here. So you've got a double level of neutral buoyancy spreading there with two separate umbrella clouds. But this is what disperses the ash. This is what makes the enormous spread of the Toba ash cloud. Imagine the size of that thing must have been to go all the way from China to Africa. You get the idea of the sort of spectacular nature of these large eruptions. So what would this do? You know, what we don't know is we don't know much about how often this has occurred. We have I think I've tried to tell you, we have a very poor idea of the volumes and masses erupted. And we also don't know how much sulfur and other gases will be released into the atmosphere. I might not say too much about this, but you can ask questions about it if you want, because in terms of most eruptions and their effect on the climate and the weather after eruption, it's the sulfur gases that are released that are important. But the story for these super-eruptions may be different. What we do know, the deposits covered huge areas. There were large mass eruption rates, which figure into how long these eruptions might last. The details of some specific case studies, and we've got lots of recent small eruptions to sort of try to scale up from, but we wonder how realistically you can do that. And this is a picture of Toba caldera in New Zealand, which is the result of what is recognized as the youngest super-eruption, magnitude 8, 25,000 years ago. But there may have been one in Japan 7,000 years ago. We really don't know. Okay. What would this involve? What would such an event involve? Well, it will involve a caldera. If you lived where the caldera collapsed, sorry, that's a pretty big landscape change, right? There would be pyroclastic flows out to 50, 80 kilometers, so they would have a regional impact with everything wiped out. There would be a widespread ashfall deposit, which could be countrywide or continent-wide, and there would be gas release, which might lead to atmospheric aerosols, which will give you, depending, as I said, where the volcano is, a hemispheric spread or a global spread for those aerosols. Here's a map of ashfall from the eruption 39,000 years ago, just west of Naples. And every year there's a new paper documenting further and further ash, ash further and further from the caldera in this southern Eurasian region. If you've got an eruption of this size, it would cover California in a layer about 1.25 meters thick. Okay, if you spread the ash over the size of California, you'd have that much ash lying on the ground all over the state. That's quite interesting.
So
And then-
those contours are meters?
These
of ash.
contours are centimeters.
Or centimeters.
These contours, sorry, yes, very good. contours of centimeters of ash fall. Yeah. And then there's these enigmatic maps that were produced by the USGS 50 years ago, but we really don't know what data they were based on or anything. But they show Yellowstone ashes, they show St. Helens, they show Long Valley ash here, this one here, Bishop Tuff, 700,000 years ago. And then they show the 600,000 Yellowstone and the 2 million year Yellowstone ash blankets. And they show that they cover the whole of the US essentially, or at least the US up to the Mississippi. And we're not sure, the guy who made these plots, whether the edge of his plots were 2 centimeters thick or 5 centimeters thick, probably something like that. But the ash would be right after an eruption, you would get ash falling outside of these envelopes here, which would, if this occurred in the US, again, would be a major disaster, right? If you had ash spreading over the whole continent, it would be amazing. So, you know, perhaps we do, even though these eruptions are very infrequent, we probably do need to know a little bit more about it. Ash is very dangerous. Huh? These are buildings on Clark Air Base after 3 centimeters of ash and a bit of rain. If it rains after the ash fall, it doubles the density of the ash, and roofs aren't made to put up with ash. They're made to put up with rain or maybe snow, but not ash, and so they collapse. So you get a lot of collapsed roofs, and unless you sweep it off buildings as it's accumulating, then it's very easy to get damage from ashfall. It's ash in the air is an aircraft hazard, and I'll talk about this at the very end. I've got a minute. On the ground, it's a respiratory hazard. It can have cristobalite in it, which is a carcinogenic component. So there's a lot of work being done on that at the moment. And ash on the sea surface can have profound effects. I won't say anything more about this, but there's been several papers about the effect of laying an ocean-wide ash blanket on what it might do to the biosphere in the ocean and the circulation. So now let's turn to the question of aerosols, because this is how most eruptions affect the atmosphere. This will be the long-lasting 3-4 year effect of a big eruption if it produced sulfur dioxide, right? If it produces sulfur dioxide and the ash cloud goes up and there's an umbrella cloud in the stratosphere, then H2O will convert to sulfuric acid, right? And sulfuric acid will form an aerosol. You know what aerosol droplets are like from aerosol cans, very, very fine droplets. But these droplets have an average size of about 0.5 micron, and they are a very effective block to incoming solar radiation, okay? And so they either reflect the solar radiation back to space, or they absorb it into the structure of they absorb the energy in the aerosol cloud. And the result is that you get less solar radiation hitting the surface, and the surface cools. There are other effects, like the northern hemisphere will respond like this. The southern hemisphere is much more complicated because it's dominated by ocean. But maybe chlorine is also important, and oops, go back, come on you. Maybe chlorine is important because it can combine with water from the atmosphere and form, hydrochloric acid. But there's no instruments up there to detect hydrochloric acid aerosols, so we don't know much about them. Some people, some atmospheric scientists have written extensively about them, like Texter et al. 2004, but they've been kind of ignored. We don't know much about the effect of other aerosols other than sulfuric acid. Okay. This is a Pinatubo picture from an early satellite that detected aerosols, and whoops, this is a pre-Pinatubo picture of aerosols in the atmosphere, some spreading around in the north and south, but very, very small amounts. The more orange and red it is, the thicker the aerosol cloud, the more particles there are up there. So right after Pinatubo, you've got a global belt. This is up to July 1991, a couple of months after the eruption. This is up to September. This is about 3-4 months after the eruption. It had already spread around Earth and was beginning to spread polewards. And then this is 9 months after the eruption. 7 months after the eruption. You've basically got the whole globe is covered by an aerosol cloud from Pinatubo, and there's pictures of it from the space shuttle. This is the stratosphere, clean of particles. This is the top of the troposphere, full of cloud, and this is the aerosol layer at about 22, 23 kilometers from Pinatubo, as viewed from the space shuttle. So it's a visible thing. It's a barrier. It's up there from sulfuric acid formation. And we've known about this for a long time, but we've not had very good images of it. We haven't had any big eruptions this century. We've had one last year, at the beginning of last year, in Tonga, which is a very peculiar event. I can talk about that if you want to ask me questions. But in 1883, having heard that Krakatoa was exploding, the Royal Society of London sent a guy out to sketch the sunsets with pastel colours. And they hired him, and he went out every day and drew what he could see over London for the sunsets. And of course, the aerosol clouds affect the pathway of the sun's rays through the Earth's atmosphere, and you get very brightly lit sunsets and sunrises. And so these were collected and put into a Royal Society report. So we've known about this for a long time, but the true importance of this to super-eruptions is a little bit certain. Just mention this, and then I think I'll stop. I have tried to reconstruct here the environmental effects of the most previous sort of big eruption in 1816, okay, Tambora. The British landscape artist, Turner, is well known for his crazy sunsets. And I think he was sketching and collecting information for paintings in the years after Tambora, 1818, 1816, 1817, 1818, early 1820s, right? This picture, and he worked by collecting sketches and then assembling them all together in paintings that he tried to sell or get into museums. And this is a picture of the sun going down over a river in southern England, and you've got this bright spot up in the sky, which is a known phenomenon with aerosols in the atmosphere. This is a secondary sunset or secondary glow in the atmosphere, which is a result of having aerosols. So it's possible that Turner and other artists working at the time were recording this without even knowing, because nobody knew that Tambora had happened for months after that. Nobody in Europe knew that Tambora eruption had happened for months afterwards. Anyway, and this was followed by a northern hemisphere really severe hardship. A guy wrote a book about it, The Last Great Subsistence Crisis of the Western World, but there's some things here about all over Ireland, UK, France, Switzerland, and even through Japan and China. There are now known to be records describing how bad it was, how much crop failure there was, and everything. So even if we got a small eruption, but of this size, we might expect similar effects from a big explosive eruption, but not super eruption. Anyway, okay. Two more features, okay? Even without aerosols, and I'll explain why there may not be big amounts of aerosol after these explosive super-eruptions. Even without this, there would be real problems globally if a large ash cloud was spread out. It can spread in 2 weeks around the Earth. Its residence time is depends on how fine the ash is. It's a big question mark. The altitude will initially be above the commercial flight paths, which are 10 to 11 kilometers, but then it would subside through and maybe spread out at those altitudes. So this ash cloud will be right in the way of where international aircraft transport occurs. You wouldn't be able to fly aircraft through an ash cloud from a big eruption like this. So whether there's an aerosol cloud or not, the effects on the aircraft are largely unknown. They've been studied by Bernard and Rose. And post-El Chichon, 1982, although it's not much published because it was mainly military aircraft that were involved, the aerosol effects on acrylic windows was epidemic and very costly to the Air Force. And we don't know much about the effects of ash, but there would be severe effects. What happens is ash is taken in with the air into the turbines of a jet. It goes through here, and the melting temperature of this ash is about 1,000 degrees centigrade, and these things run at about 1,200 degrees centigrade. And so the ash is melted in the jet, and then it's squirted out the back where it rapidly crystallizes to glass and blocks up the outlet from the jet engine. And so the jet engines fail. And we've never had a major aircraft disaster from ash in jet engines, but we've had 2 or 3 really near misses. And otherwise, ash on aircraft could have various negative effects as listed here, but a lot of these are being currently studied, but we're still a long way from really understanding what the true effects of ash, of an aircraft running into an ash cloud would be. Okay, you would hamper global transport with another big explosive eruption. Okay, my last slide. I'm always asked, well, where's it going to be? Where's the next big eruption going to be? Okay, and here's my bet. Okay, it's not Toba, it's not Yellowstone, it's not Long Valley, it's not Naples region, it's Taal in the Philippines. Okay, here's Pinatubo, here's Manila Bay, here's the southern end of Luzon, the southern end of southwest Luzon. Okay, here's Manila, where 17 million people live. And this area has been declared by the Philippine government as their sort of area for large-scale investment, for infrastructure, for growth, for economic development, right? And in the middle of this sits Taal, which is a very nice caldera, 20 kilometers across, all right? And this whole area are pyroclastic flow deposits from Taal, and we know almost nothing about them. We know age dates on them, but we know they're big because they go 20 kilometers from the caldera. And this is Volcano Island in the middle of Taal, and it's actually, it has God knows how many eruptions since the 16th century, hundreds, and it's been active in 2020 and 2021, and there was even a little bit of activity from the crater on Volcano Island this year, at the beginning of this year. So this thing is continually active, and it's telling us that there's magma down there, but of course we don't know whether it's going to be another small eruption from Volcano Island, or it could escalate into a big caldera-forming eruption. It won't be a super-eruption, it won't be a magnitude 8, but it could be a magnitude 7, and it could be a nasty surprise. And so, if you want my bet for what might be the next big explosive eruption, this is it. Thank you.
So we have time for questions, if there are any.
Yes.
Thank you, that's excellent talk. I really enjoyed it. Thanks for coming. Question I had is, in the beginning you were talking about the data and the lack of data, and this shows my naivety, because I don't study volcanoes and I study much older Earth stuff. But going back 2 million years to the Pleistocene, most of the terrestrial landscapes that were completely wiped out by glaciers are preserved. And so I forget you couldn't map out and get an accurate volume of a large eruption, but I guess I feel like there'd be enough Pleistocene to present basins preserved, or you at least know where there were thick deposits. So how bad is the record going back through the Pleistocene of large ash eruptions? Does that make sense?
Well, you've got a very valid point, and there are preservation sites, but putting together observations from a lot of different sites to show that they were or were not all produced by the same eruption or not is very time-consuming and sometimes expensive work, because it would involve coring or lake coring or something like that. So gradually we're getting a better idea of how many eruptions have occurred in the Pleistocene. But it's going to take us many decades to get there. We're not going to have a sudden sort of breakthrough of, oh yeah, we missed all these. No, I think it's one by one, region by region. As I said, every year there's a new paper pushing the extent of that 39,000 ash from the Capi Flegrei west of Naples, further out into Turkey and regions like that. But it's very spasmodic, the advances and so on. You have a very good point, and we will eventually get a much better picture. And while I'm answering this, I'll mention this 7,000. I kept mentioning this 7,000-year eruption in Japan. It's not real, well, it's offshore Japan. The caldera is a submarine caldera, and you see a little bit of the rim of the caldera above sea level, forming an island. All the deposits are underwater. Okay? The caldera is big enough to have produced a magnitude 8 eruption, just. But, and there's, you can argue about size of caldera versus size of eruption, but there's a very broad correlation between the two. The biggest calderas form from the biggest eruptions. Quite simply, the work hasn't been done to find these submarine deposits and sort of stuff them back into the volcano to see how big it really was. So there's a widespread ash fall over Japan, and that's been mapped from this event, but that's only part of the volume. What about the pyroclastic flow deposits offshore, underwater? We just don't know about them. So there's a lot of work to be done in order to build up a better picture. Thanks, it's a very good point. Yes?
I might have misunderstood it, but in some of the factors that distinguish the big 6s and 7s and 8s, I think you said that magma composition didn't really matter and that blows my mind. Why? And that destroys a lot of my 101 lectures. Thank you. Because basaltic or very mafic magma compositions shouldn't produce.
No, they don't.
Okay. Well, I thought that's what you were saying. That there
No,
was.
sorry, I
Maybe I
gave the wrong
misunderstood.
impression. But for the felsic magmas, whether it's a dacite, whether it's a biodacite,
Yeah.
whether it's a voluminous rhyolite or high silica rhyolite, they don't really matter.
I got you.
Okay.
I got you.
Have
the
there been
felsic
any? If I'm right about Tal,
Yeah.
its ignimbrites are andesite.
Oh, intermediate.
Okay? There are very few andesitic eruptions of this sort of scale ever described. I think there may be one or two in the Andes that have been described of like magnitude 7. But I should have prefaced what I
That's
said.
all right. No, okay, but from intermediate to felsic, it doesn't matter. You can have big ones that it doesn't distinguish whether you're more felsic or more or intermediate.
Yeah, yeah.
Okay.
And, yes, sorry, go on.
I'm kind of curious, what's your perspective on the idea of extinctions, mass extinctions associated with volcanics of one form or another, like the Deccan perhaps,
Okay.
or other areas? basically saying
Well,
is
these
that
are explosive eruptions, and the Deccan traps are largely lava-forming eruptions. We don't find much evidence when we go to the Deccan of explosive events accompanying those lava-producing eruptions. So we'd be looking at mechanisms of eruptions like the Columbia River basalts or like Iceland to release gas and produce climatic disasters from the release of gas from those eruptions. Certainly basalt magmas have more sulfur, and so in terms of sulfur gas production, they could be responsible for injecting a lot of sulfur into the atmosphere and causing climatic disasters. But the whole thing about mass extinctions and volcanism resolves around this fact, that there have been 5 or 6 major mass extinctions in the last 300,000 years. All of them have been accompanied by a flood basalt producing event, a large igneous province, a basaltic large igneous province. One of them, the Deccan, also has a meteorite impact, okay? And everybody says that the mass extinction 66 million years ago during the Deccan period was caused by the meteorite impact. Probably, it probably did. But what about these other cases? You know, one case of a coincidence is okay, but it's a coincidence. But 5 times in Earth history has there been a major mass extinction and a flood basalt province going on at the same time, happening at the same time. And both are very I don't know what the word is, both are kind of quasi-periodic events during Earth history. We only get a flood basalt event every 10, 20 million years, something like that. The most recent being Columbia River, 15 million years ago. Probably can't expect another flood basalt province to crank up in the next few million years. But it's a mystery. I haven't solved it. There are a lot of people thinking about it, but I'm not sure what the answer is, why there are these 5 concurrences of mass extinctions and large lava forming eruptions in Earth history, and only one meteorite impact. Yeah, sure, it does a lot of damage, but did it just happen at the same time as there was a flood basalt province occurred? Probably.
I have one last question. That is, you mentioned